Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to have a session on Green's theorem. So before that, we were talking about vector fields and conservative vector fields. We talked about, um, I think we did the curl, we did the divergence. So today we are going to see how Green's theorem in 2D simplifies many such line integrals. So if you remember when we said the integral of f dot dr, now we are going in Green's theorem, we are going to say, okay, here we have a curve, right? And this curve is simple, meaning it doesn't make holes or it doesn't intersect itself. It's simple, and um, it's also closed. And to show that it's closed mathematically, we draw like a circle around the integration sign. Okay, so that means it's a closed curve. And if f can be written as, usually if you look at the book, it tells you it uses P and Q, but since remember, we used M for the X component, N for the Y component, and P for the Z. We don't have a Z because that's a 2D. So we are going to write it as M dx plus N dy. Green proved that this can be rewritten as a double integral. You say, it's a single integral, like line integral. Why would I make it double? Yeah, you will see why it makes things much, much easier and less cumbersome. So it's the double integral over a region, meaning you can find the limits of integration, the x and the y, whatever, of, do you remember the curve? Let's do it so that you don't memorize anything. You see how it's done. To calculate the curl, remember it's a cross product between the del operator and f, right? So I have I, j, k, and then partial x, partial y, partial z, and then I have m, n, and since we are in 2D, it's a 0 here. Now there is no reason to make it, use the duplicate column method, because you will see that if you take the partial with respect to y of 0, you get 0. And if you get the partial with respect to z of n, since we are in 2D, this n would be either x or y. So the partial with respect to z is 0. So the I component is 0. Similarly for the j, you take the derivative of x with respect to 0, you get 0. You get the derivative with respect to z of something in 2D, x or y, or both, you get 0. So it's only k. It's only k. This times that, so it's partial x of n uh, minus partial y of n. That with respect to k. Of course, we are not going to write k because we know we need just like if you looked at torques and my session in the engineering statics, we discussed that. And if I remember correctly, I told you that always think of, say, a can with a bottle can, or like a nut with, no, it's easier a bottle can. If you rotate it counterclockwise, it moves up in the positive k direction, and if you turn it clockwise, it goes down in the negative z direction, or k, negative k. So we are going to consider if the if the flow is rotating counterclockwise to be positive, if it's clockwise to be negative. So we said my function has two components in the x and the y. Both of them are, they can be both containing x and y. I'm not saying this is with respect to x and no. I'm saying m is a function of xy, n is a function of xy, meaning we are in 2D. And these two, m and n, are differentiable. And this function, this curve that is closed, is simple and it doesn't intersect itself. Then we can write this, you see, partial x n minus partial y m d area, which can be written as integral of nx, just for simplicity, minus m sub y, meaning derivative of n with respect to x, derivative of m with respect to y, dx dy, or dy dx. Oh, the only thing you need is just limits of integration. And this makes life much easier in many problems. I prepared 3 examples for you. We are going to go over them, and we see if we didn't have Green's theorem, what would happen. Okay, here is the first one. We want to evaluate the line integral of xy dx plus x squared y cubed dy, where my curve C is just a triangle with vertices at 0, 0, 1, 0, and 1, 2. And the problem tells you that the motion is counterclockwise, so it's positive. If it was clockwise, you get the negative answer, so it's not hard. You can solve it as if it were counterclockwise and then multiply by -1 in the end if it confuses you otherwise. Okay, so now we are going to say, okay, here is m and here is n. Remember, we take the derivative of n with respect to x minus derivative of m with respect to y. And we saw y because that's how we calculate the curve, the cross product of the del with f. So now we can find partial m, I'm sorry, partial, well, we can do both. But usually we start with the n and then we subtract the partial with respect to y of m. So when you take the derivative with respect to x, you get 2xy cubed, 2xy cubed. And when you take the derivative of m with respect to y, you get just x. Okay? So now we are going to say, okay, first I need to find the limits of integration. You can see that the y starts from 0. So when I write the double integral, I will start with y in the beginning, in the inner integral, goes from 0 to this line. But what is the equation of this line? That's a straight line passing through the origin, so there is no y-intercept. And its slope is 2 over 1, since it starts from the origin, so it's y over x. Delta y is 2 and delta x is 1 anyway. So goes to 2x. And the x goes from 0 to 1. Now, partial n partial x is 2xy cubed minus x dy dx. You can, so here we are going to take, if we take the derivative with respect to x first, then I would say I'm going from y over 2 to 2, that's the x, and the y would be from 0 to 2. And you get the same result. So it's up to you to see. Sometimes when you change the order of integration, you simplify the problem. But here, let's do, notice that if we don't use Green's theorem, we don't use the double integral, you have to find the line integral for this line by itself, and that line by itself, and that third line or hypotenuse by itself, and then you add them all 3. So you have to do 3 times the work in that case. Here, the double integral simplifies things, as we said. So if we take the integral with respect to y, I will get the integral from 0 to 1. And then when you integrate that with respect to y, you get 2x y to the 4 over 4 minus xy, and they are evaluated from 0 to 2x. The 2 and the 4 would make that 2. And then if the y is 2x, this would be 16x to the 4th divided by 2 would be 8x to the 5th, right? The y to the 4 is 2 to the 4, x to the 4. 16x to the 4 times x is 16x to the 5th over 2 is 8x to the 5th minus 2x squared. And you are taking the integral from 0 to 1 of this thing now with respect to x. I'm sorry, I forgot to write the x here. So you will get 8x to the 6 over 6 minus 2x to the 3rd over 3. Everything evaluated from 0 to 1. I don't care about the 0. It will give me 0. But when I do the 1, I will get 8/3, which is 4 over 8/6, I'm sorry, which is 4/3 minus 2/3 equals 2/3. And that is the answer. That's what we call the circulation. That's the total curl, meaning around the edges. Okay, it's not a curl at a specific point. No, that's the total. And you can see that it really was so simple. I solved it only for the whole thing once. I don't have to do it for each side separately and then add at the end. You can take it as an exercise for you to calculate the line integral for each side and add them and see if you get 2/3. When we move to the second equation, similar, but now we are going to do the line integral. We want to evaluate the line integral over a circle of radius 2, centered at the origin because it's x squared plus y squared. So like before, we are going to call this guy m, this guy n, and we can say nx, which is partial n partial x. That's the meaning. When you take the derivative with respect to x, you get 1. So easy. Partial m partial y, which is the my. Okay, when you take the derivative of m with respect to y, you get -1. So nx minus my would be 1 minus -1. And then you take a double integral dx dy. Here, I've seen people do it, taking, like we did the previous problem, you take, you transfer the x and y into r and theta, and dx dy would be r d theta, and do all this stuff. You don't need that. I will tell you why in a second. This is the double integral over the region of 1 minus -1 or in 2 dx dy. I want to ask you a question. A2 is a constant, I can take it out. What's the meaning of taking a double integral of dx dy of that circle? Anyone knows? I bet you do. Yes, it's the area of the circle. Notice that I don't have any x's or y's. It's a constant. So it's a waste of time to say, oh, this equals the double integral of r d theta. No, don't. It's 2 times the area of the circle. It's that simple. Think about it. Try it even. Try to integrate r d theta, r going from 0 to 2, and theta goes from 0 to 2 pi. Absolutely, you will get 2 times pi r square, which is 4, so you get 8 pi. See how simple it is? You don't get an easy problem like that a lot of time, but when the integral here, nx minus my, is a constant, there is no need to integrate. It's like when I tell you, find the area of this triangle. Nobody would say, oh, take the double integral from 0 to 1, 0 to 2x of dy dx. Of course, you will get the area of the triangle, which is 1/2, base, which is 1, height, which is 2. So you get 1. I don't need to integrate. You see, we don't do things just because that's what the law says. No, you think. You think you can make many problems much easier if you think about them first. Okay? I hope this is clear to you, right? Absolutely, you can check. Take the integral of RD theta or 2 RD theta, make R from 0 to 2 and theta from 0 to 2 pi and see what you get. Just to be confident that. Okay, that's the third and last one. Here we have a rectangle. And this rectangle, it says, okay, so let's do it. And we say this is 1, 1. This is 4, 1. This is 4, 5. And this is 1, 5. And they tell you it's counterclockwise. In fact, I forgot to tell you that the previous problem was also counterclockwise. If it were rotating clockwise, the answer would be -8 pi. It's the same thing. Okay, positive is counterclockwise. Okay, like we did before. So now it's it's a repeat, but one time it was a triangle, one time it was a constant, so you don't need to integrate, and now it's a rectangle, so we'll see how we do that. Partial n partial x, which we call n sub x, or most books would call that q sub x, and p sub y. They call this p and this is q, but since we started by referring to this as m and n, then I'm just trying to be consistent so that you don't get confused. When you take the derivative of n, so let's say this is m, this is n, with respect to x, you get 0. And when you take the derivative, if the derivative of m with respect to y is 0, what would that be? Yes, conservative. Conservative field. Doesn't have to be 0 if they are the same value. Notice we subtract them. So when you subtract them, you get 0, and the integral of 0 is 0. And that's why when we say we have a conservative field, the curl would be 0 and the circulation would be 0. And because remember we said, okay, I don't want to go more into that, but that will not happen here. But if it happens, if they are equal, we know they are conservative, and if the curve is closed, you get 0 circulation and 0 curl. Okay, so the derivative of m with respect to y is x squared, right? So now my integral, double integral of dn dx, which is 0, minus x squared dx dy. It doesn't matter, you can do dx first or dy first, but if you take the integral with respect to, that's a rectangle, so the integral is from 1 to 4, right? And the integral of y is from 1 to 5. So here you don't have to find functions, and that's why you can do the integral in any order. So if we take it with respect to x first, since we have the limits of x inside, you get negative x cubed over 3 evaluated from 1 to 4, and then the integral from 1 to 5 dy. Notice that would be a constant, so you will end up with y, meaning you are going to multiply by 4 at the end. Anyway, so negative 81 third 4 cube. I'm sorry, 64. I did 3 to the 4th. I'm so sorry. So 4 thirds, 4 to the 3rd power is 64 over 3 minus, and then when you take the integral with respect to 1, there is another negative sign. Notice it's this minus that, but this thing is 1 cube over 3 times 1, so negative 1/3. integral from 1 to 5 dy. Okay, negative times negative is positive, so you get negative 64 thirds plus 1/3 is negative 60 thirds, which is negative 21. So you get negative 21 integral from 1 to 5 of dy, meaning you will end up with negative 84, right? So you get negative 21 times y evaluated from 1 to 5 equals negative 21 times 5 minus 1, negative 21 times 4, negative 84. And that would be the line integral of this function. I think that's enough, but I want to tell you that this formulation of Green's theory is transforming the curl into what we call circulation. There is another form. So that can be written as the integral of f dot t, meaning tangential force in the direction of the curve ds. There is another form that relates the divergence to the flux. When we talk about the amount of the flow that goes outside of the area, not around the area, but goes outside, like the divergence. And again, the right-hand side would be the divergence, the left-hand side would be what we call the flux. So it comes really in two flavors. Next time, maybe I'll prepare a couple of examples that we go over to see how it's similar, but of course, we are not going to say nx minus my. It's going to be the addition of those, not the difference. Anyway, I hope this was easy enough for you to follow. If you have any questions, please let me know in the comment section and I will try to get back to you as soon as I can. Thank you very much for your time. Hope to see you soon.